Good afternoon. It is my pleasure to talk to you about hardware-in-the-loop solutions, in particular introducing AutoHawk. Why are we looking at HiL? Don't worry, I will not read the entire statement here from a recently published Frost & Sullivan report on the HiL market. Instead, I would like to summarize the essentials from that. The HiL market is a sizable and high-growth market, which is critical for driving innovation. It is aligned with industry trends for electrification of vehicles, for example, and of course for the massive introduction of advanced driver assist systems. It is synergistic to simulation and simulators, and we would like to therefore leverage our core strength and provide high-class products and services to help our clients to drive innovation. Initially, ViaGrade is focusing on three main application areas, and you will see more and more solutions developed in the area of chassis engineering, including steering systems, passive and active suspension components, brake systems, and all its associated controllers. We will also look at the area of advanced driver assist systems, with particular attention on sensors such as cameras, radar, LiDAR, etc. And thirdly, we will look at the area of powertrain, and here in particular regarding the electrification. Let me point out that in particular the electrification has impact on the rest of the vehicle, as you are all aware, with respect, for example, to steering system and brake systems, for energy recuperation as one example. All that results in a need for more complex models, where all these models are put together and running either in real time, as model in the loop, software in the loop, hardware in the loop, human in the loop, or a combination of all of that. So complexity is increasing for the simulation and the tasks we have in front of us. What is our vision? The vision is to have an integrated virtual test approach. Hardware in the loop solutions are an essential part of it. Applications allow our customers throughout the development cycle to decrease the number of physical prototypes and to achieve virtual sign-off. During product development, controllers and hardware components become available and need to be included in simulator testing activities. Let me pause here for a second. It is based on our experience often the case that during the development, the software in the loop solution, which is often preferred, and we're coming with a strong simulation background, the software in the loop solution is not feasible because you may work with a third-party supplier who's not willing to open up his IP to you, and the only way to get an overall accurate model description is by including a controller as it is available in the real car on an ECU. So in some cases, in order to get overall accurate results, we have sometimes no other solution than including the ECU early on in the process. And that is where we believe having a consistent way throughout the development process is an added feature of our solution. So ViaGrade HiL solutions enable customers to use the same real-time tool stack for different simulation activities like software in the loop, model in the loop, hardware in the loop, on the simulator, on vehicle testing, for example. Now, I'm proud to introduce AutoHawk powered by Concurrent Real-Time to you. Let me summarize what AutoHawk stands for. AutoHawk is the VI-grade HiL solution powered by Concurrent Real-Time for automotive applications. It consists of real-time hardware, the real-time operating system, real-time software, and I/O cards, all what we know from Concurrent already. It is highly configurable. VI-grade real-time software, all software from third party can be installed on it. In the same configuration, it can work as standalone Linux-based high-performance computer, as an HiL system, or in combination with a driving simulator or on a real vehicle. All in all, AutoHawk is a flexible HiL platform that can be used across the entire product development cycle from concept to sign-off. Let me start out with some solution highlights. AutoHawk hardware is based on commercial off-the-shelf components, thus allowing to take advantage of the latest chip developments in the market at an attractive price point. Of course, that's valid for I/O cards and other components as well. The leading real-time operating system is based on Linux and provides an open architecture which makes the integration of your custom solution as well as third-party products from software to special I/O boards much easier. But probably one of the most attractive details is the multi-core technology that provides for more computational power and allows you to run more complex models and controllers all in one system, avoiding problems related to operating a network of less powerful real-time systems. Simulation Workbench provides the platform to integrate the models, so the solution does not really require Simulink. However, another highlight of the solution is that it's tightly integrated with Simulink, such that you can run it directly on the real-time system without the need to transfer code from a client to a host file system. Of course, common automotive communication protocols are supported, such as CAN, CAN-FD, LIN, and a number of others. AutoHawk supports the VI certified ecosystem. So in other words, you can run a lot of third-party products on our system that are certified, and we're trying to make sure with our partners that you can rely on the quality of these components running on AutoHawk. The open architecture with ASCII data structures and configuration files, as well as the C, Java, MATLAB, and Python API, make it very easy to integrate with in-house tools and processes for test automation or data logging, for example. Last but not least, it is VI grades and Concurrent's multi-year expertise to connect HiL systems with simulators that make the solution of complex systems possible. Now let me outline a little bit how we see AutoHawk being used from concept, so anticipation of an idea, to final sign-off. In an early stage, you can look at the system as a desktop system for offline simulation with software in the loop, model in the loop applications. So AutoHawk is used for offline simulations, controller development, and taking advantage of the performance also for design of experiments and optimization loops. What are the benefits? Well, you use the same machine and tool stack that can be used for HiL and driver in the loop, and you get closer to the simulator and HiL applications with a reduced investment early on. The second application area is, in our perspective, the in-lab application, which is HiL, SIL, and MIL. So these are the typical HiL applications in which a device under test, could be a steering system or an ECU, is connected to AutoHawk running real-time software. You may do fault injection or include test automation. All of that is possible. What are the benefits? Well, clearly the typical benefits of doing HiL in the classical sense, but also during this phase, the device under test can be optimized and tuned prior to connecting it to a driving simulator for further tests. Now we come to the domain that, of course, ViaGrade has been active in for a long time, which is on-sim. These are HiL applications in which the driver sends inputs to the AutoHawk through the simulator. It is particularly useful to test corner cases and where the closed-loop inputs are essential. But let me step back a little to a comment I made earlier. In some cases, the HiL aspect is required only to get very accurate model behavior of the overall vehicle, and so even when the ECU is not the focus of the engineering question, it is an essential part in order to have accurate model representation. What are the benefits? Well, you can test, as mentioned before, corner cases and develop those also for offline simulation. So by recording those cases, you can use them also in the offline world. Now let's go and look at on-vehicle testing. These are HiL applications where virtual vehicle models run on the real vehicle with mutual influence. What are the benefits? The virtual vehicle on AutoHawk runs about 5 times faster than real-time, can provide inputs for the real controller. The real controller can also be fed with a combination of real-time channels coming from both vehicles. So in other words, from the virtual vehicle, used in a predictive manner, as well as the real vehicle coming from actual measured sensors. All that opens up the door for totally new possibilities of controllers. And lastly, you can also use it in the area of for the digital twin application, where the driving simulator and real vehicle are fully synchronized and they affect each other. AutoHawk comes in 3 standard configurations with 8, 16 and 24 cores. It is equipped with a 2 terabyte SSD hard disk to manage your projects and log data. One could say you have a pretty powerful data logging tool also at hand when you get an AutoHawk system. All systems come with a communication card that support CAN, CAN-FD and LIN out of the box. AutoHawk runs with a Linux-based RedHawk operating system and simulation workbench. And for on-vehicle applications, the systems are also available in rugged chassis. The systems are highly configurable and provide 4 to 7 slots to include boards for I/O. The most versatile being freely programmable FPGA boards. Of course, you can also include an expansion chassis for signal conditioning and fault insertion, along with a programmable power supply, as you can see here on the top right. Let me outline one of the more attractive pieces of the offering, which is the freely programmable FPGA board. It's based on the ARIA technology, and we have 3 sizes, the A5, B3 and B7 size, where the B3 and B7 are for high-end, while the A5 is reserved for the so-called, what we call the multifunction predefined cards. You can see here the general specifications with, for example, 16 16-bit analog input and output channels, supporting PCI Express. And we have a number of fixed functionality boards, as mentioned before, but also freely programmable boards. In order to make it easy to take advantage of this technology, a number of predefined IP core modules are defined and available. In those cases, this FPGA board is already pre-configured to solve to deliver particular solutions. For example, for ignition injection, or for an send in out, or NOx sensor as one example, or in a more generic way for the electric drive with models for inverters, for motors and controllers. And perhaps at this point I should highlight one option of that is the capability of including a JMAC RT model in the system, and that is unique as far as we know, a unique offering in the world right now, as that you can get out of the box. The generic FPGA Workbench architecture looks like this. You have either the capability of freely define your own capability on the FPGA card using FPGA Workbench. In that case, you will use your own compiler that we also provide, which is the Intel Altera Quartus Prime system, which is required then to generate the code for the actual FPGA card. And also running on the AutoHawk system then is then either the predefined capabilities that I listed before. They are fully integrated in Simulation Workbench, where you then only have to set parameters and configure these sensors and I/O characteristics for these modules, or you can run them through custom applications. AutoHawk applications are what is driving us, and as you know, we have defined 3 standard configurations: AutoHawk 8, AutoHawk 16, and AutoHawk 24. And we classified them based on our years of experience of what typical models require in terms of compute power. So the AutoHawk 8, for example, is a typical size machine where you run real-time offline simulations with VRK Real-Time. You take advantage of the compute power to run design of experiments and optimizations. It's the system that you use for standard ECU testing with VRK Real-Time, where VRK Real-Time is running with standard tired models, or it is the system that can be used for chassis HiL, for example, when you connect it with a steering or brake test rig. Perhaps I should also point out the AutoHawk 8 is what is typically included in our compact simulators. The AutoHawk 16 has additional compute power that is needed, for example, when including more advanced tire models, where each tire has to be solved on an individual core. That's something that all our partners are supporting, like F-Tire, CD Tire, Swift, and others. Another reason for more need of computational power is when looking at ADAS applications, where you run with multiple agents and you have more and more sensors integrated into your simulation. Lastly, of course, there are complex powertrain driveline applications, in particular around eDrive with battery management and the like. And for the high-end applications, we have an AutoHawk with 24 cores. That is needed, for example, when running advanced explicit multi-body simulation models, so like SimPac or Adams Real-Time, and it is used for special applications, for instance, in vehicle testing. AutoHawk in general consists of a layer of hardware, which is essentially the well-proven real-time system from Concurrent that is also running in all our simulators, as mentioned before. It comes with software including VI Drive Sim, with the vehicle model and virtual driver in VRK Real-Time, and the virtual sensors, environment, traffic, and scenarios in VR World Sim. Of course, running third-party software and extending systems through the FMU interface is possible. All that is integrated with Simulation Workbench and its real-time database. Users may choose to automate testing using either the Simulation Workbench scripting capabilities or connecting it with the existing test automation tools through the available APIs that I mentioned before. The device under test is then connected through available communication protocols such as CAN or through the customer's specific I/O boards. And in order to get the human in the loop, the system can be integrated with a simulator, which provides great value, for example, for defining and testing corner cases. Now, let me introduce to you the concept along a simple demonstrator. What do we have? The scenario is the following: is the development and functionality validation and subsequently calibration of a stability controller. This demonstrates how a system like this can be used to get the controller better prepared before connecting it with a simulator, or even before going on the track with a real vehicle. Let me start out to describe the general workflow of this. So first we will have to develop a normal vehicle model and set up the maneuver in car real-time. We have to create a control system, come up with a design of a controller, then do initially software in the loop testing in a more traditional way, and then using co-simulation between car real-time and MATLAB for that. And in the last step, we will look at that integrating the actual ECU with simulation Workbench on AutoHawk. What are the steps we need? Well, we're using the proving ground of VI WorldSim. The maneuver is a simple lane change maneuver that is often referred to as a press maneuver because it's often used to rank cars based on the quickest time against the competition in the auto press. Then we're using, in that particular case, a standard vehicle, and we perform the lane change at 90 kilometers per hour. With a passive car, it is impossible to pass the test, and by reviewing the results like yaw angle, rate, or steering angle, we can start developing an idea of what a controller should look like. In our particular case, we came up with a simple example. So here you can see a typical MATLAB Simulink session that is used to develop the controller and to define the communication interface with the vehicle. We are using the car real-time, as mentioned before, as the vehicle plant model. That's the little block here in the middle in yellow. And the controller is very simple, acting on the brakes just for demonstration purpose. The controller is using the vehicle speed, driver steering demand, yaw rate as inputs, and acts on the brake pressure. In real life, this would be more complex, and additional sensor data like wheel speed would feed in, of course, but for the demonstration purpose, we tried to keep it simple. Using the traditional software in the loop method, the control system can be tuned using VI Car Real-Time together with Simulink, and it's contained DOE and optimization methods. Up to this point, you can either do that work on your normal Windows PC, so that's the standard offline, or already at this point, you can take advantage of the high performance compute power of the AutoHawk system and move everything onto the AutoHawk, and thus shortening the experiment cycle. Now we move to the AutoHawk system and we set up via drive sim session. So the maneuver is performed on a wet surface that has to be defined in order to allow users to interactively tune the system. We have also included a little dashboard on a touch screen using our VI dashboard tool. You may also use the HMI capabilities that are coming with Sim Workbench. And in this particular case, on this little screen that you can see here on the right, that's the little dashboard, you get a collision warning, for example, sign if there's a collision occurring. So what is the HiL machine look like right now? It's an AutoHawk 8 system. We have in that particular case also included the Windows PC in order to visualize a little bit more. But in that spot, you could easily imagine that an expansion chassis would be fitted there for signal conditioning or fault insertion. We have used a programmable off-the-shelf ECU that allows us to run any kind of controller, from an eDrive controller to vehicle dynamic controller on it. In this demo, we use an ESP kind of controller. Then the programmable AutoHawk power supply is connected with the ECU, and in that case just provides 12 volt. but can be used also for interrupts, etc. The messages are exchanged between the ECU and the AutoHawk via a CAN bus. The control system will take inputs from the AutoHawk and will send back control signals. The control signals in this case are the brake moments. And what we have done here is we even hooked up, as I mentioned before, this thing to the dashboard. So while the simulations are running, you can interactively change parameters in the controller during the simulation. So what is really needed for that? What is contained in such a project? If you set up a simulation workbench session, kind of an integration layer, you have always a combination of scripts, models, and a so-called real-time database into a full simulation. In this particular example, I will show you a couple of snapshots later. We have 3 processes running on different CPUs. So via car real-time, so the vehicle model. We have 1 process running the dashboard and 1 process that's running the world environment. The test session, in each test session, simulation parameters must be specified, for example, maximum overruns, consecutive overruns, etc. So these are generic kind of parameters that you need to set up your session. It always has to include a so-called real-time database. That's a collection of I/O points which can hold numeric, Boolean, or string values. And essentially, it's a mapping of these points to hardware registered or message fields. It has optional conversion functions that convert between the raw hardware layers and the engineering units of the I/O point. Lastly, you may include scripts. And in that case, we are using a script to automatically reset and automatically rerun the simulation at each end of the path. Here you see a typical snapshot of a sim workbench session. One perhaps thing I would like to highlight here that, of course, as you set up your test session, there's a capability to import DBC files, so the normal way to defining your CAN bus. And that there are a number of tools available to do that and to make it convenient for you. And like I mentioned before, also in sim workbench, you may use its own HMI sim workbench tool or via a dashboard. I only put this up here to give you kind of an idea about the interactive solution that comes with the application. On the left-hand side, you have a tree view through which you can navigate. You have a test area here, the real-time database as you define it, scripts, and the different types of models and some more capabilities. As mentioned before, you have to define the different processes and models. So in this case, for instance, we have 3 of these processes and models for car real-time. You can see a little detail like it's located on CPU number 2. We have the dashboard running on CPU number 4, and we have WorldSim running on CPU number 3. That's a typical example. It can be many more processes that you can manage that way. Of course, you have the real-time database defined and the scripts again here on the left-hand side. Those are the ones that make up a test. In a test session, you can, of course, when running a simulation, also monitor the evolution of your CAN signals. And there's also other plotting tools and monitoring tools available. But here you can see one way of looking at the CAN bus acting during the simulation. Hope it was possible to see even in this GoToWebinar. You can see how the different inputs and outputs on the CAN bus are changing. The real-time database, to dive a little bit deeper in that, as I mentioned before, acts like a bus system if you want. It's a mapping capability, and of course the user can set up communication with the RTDB, so with the different real-time database entries via a number of protocols, and just mentioned before already, including CAN, CANFD, LIN, but also EtherCAT or other protocols in that domain. And lastly, I would like to point out the capability of scripting. So I mentioned before for test automation, and here again we used a very simple case. If you want, this is a while loop here in this case. So this thing keeps running until a certain condition is met, which is either pushing the button or a certain condition of the simulation has been reached. So this gives you a very powerful mean to run and control all your simulations on the AutoHawk system. Here I would like to give you an example of how the system signals are looking. We're looking here at the throttle, we're looking at the yaw rate, and the steering effort or steering demand. And in this particular case, initially you see the curves for the system or for maneuver being driven without the controller being active. I let it run here for a little bit. Of course, that is something you can monitor live while the system is running, and you can monitor, of course, these signals all the time. And then once the system is turned on, you can see the steering effort and the yaw rate is dramatically reduced. And that shows you the functionality in that particular case of the controller acting on the vehicle. So here you see a summary from the perspective of looking through the car. And here on the right hand side, that's the dashboard that we talked, where you can turn on and off the controller and see how the vehicle then is basically not able to pass without hitting the cones. And if you turn on the ECU, you can start interactively tuning the different parameters. So is the intensity gain can be used to tune the intensity and invasivity of the control system. And the number 2 parameter is there in some sense to let the control system delay its intervention. On the right hand side, of course, you can see how the controller is acting on the brakes. And this is a nice way also if you want to have other people. So there you saw some collision occurred. This is a good way of tuning the system in a very interactive way before, for example, going on a test track. So we believe with the accuracy of the vehicle models, including advanced tire models, you're getting much closer to a calibration of the system prior to applying it on the test track or in the vehicle on the track. Let's look at some other use cases, and I will just touch on that on a high level. So one use case would be where the AutoHawk is connected to a steering rig, and then it is ultimately connected to a driving simulator. What are typical applications? Well, steering system integration, of course, EPS calibration, steering feel, it's very sensitive, of course, fault injection, benchmarking, X-by-wire redundancy validation, or generic ADAS development. In fact, this rig has been also combined with a brake rig in the lab. Or it could be used the system for very complex HiLs cockpits to be developed. In that particular case, we developed a solution that contained not only one bus, but 3 CAN bus and 1 FlexRay bus system, if I remember correctly. Had not only one ECU connected, but I think 10 for different domains, from chassis to comfort or ADAS type of systems into all the way to ECUs controlling, for example, the ambient light. In that particular case, a wheel speed sensor was also included. Perhaps something to point out: although Sim Workbench is fully capable of providing REST bus simulation, so there's capabilities to define basically what is running on your CAN bus, Of course, you can also include third-party solutions that are commonly used from Vector, for example, to take care of the rest bus simulation. In that case, the software that we used also included VI DriveSim and Simulation Workbench. Or just to give you another example, a little camera rig where there was a camera fixture included with lens, monitor, and also here in this case we connected with driving simulator. So what are the applications? Lane keeping, emergency braking, blind spot detection, traffic sign recognition, autopilot. Whatever you can imagine can be done with a camera. This can be done with such a system as well, in combination, of course, with VI WorldSim used to simulate the complex traffic scenarios as an example. And then in powertrain, I picked an example that's a little bit out of the ordinary, pretty extreme case. This was a very complex system which was very powerful, but the highlight of this specialty here is that it was even put into a rugged chassis or box space here, rack, that was possible to take onto the vehicle. I can't say more about these specific cases, but on generic terms, it was used for fault insertion and engine control development. At this point, I would like to conclude my presentation. HiL applications complement offline and driving simulator activities and help to achieve virtual sign-off. The demand for HiL applications is expected to grow in the next 5 years significantly. ViaGrade, together with Concurrent Real-Time, has launched AutoHawk with a complete and open solution made of hardware, software, and integration services. And I would like to point out, as we are starting and launching this initiative, you can get more info, and we will fill in more content in that area on viagrade.com/AutoHawk, and the QR code will also lead you into that landing page.